Hey guys, let's begin our last section in this set, 311 hyperbolic functions. We're going to learn some more. We're going to learn what these functions are, and then we're going to learn their derivatives. Let's jump in. The hyperbolic function. So it turns out there are 6 hyperbolic functions, and they all take the same names as the 6 trig functions. So we're going to see hyperbolic sine, hyperbolic cosine, hyperbolic tangent, right, and so on. We'll discover just why they take the same names as the 6 trig functions and even why they take the name hyperbolics kind of in our discussion. Let's begin by talking about hyperbolic sine. So first, the notation. Notice we denote hyperbolic sine as sine h of x. And you kind of see what I have written down beneath it. The formal name for this thing is hyperbolic sine of x. But usually people give it a nickname that just looks like how you would read it. So we're going to refer to that as sinh x. And there at the top is how it's defined. Sinh x is defined as e to the x minus e to the negative x over 2. Now that seems really random and kind of out of nowhere, like we're calling it by something like a trig name, but then it's also hyperbolic, so there's a connection to a hyperbola. But then the actual definition of it, it's defined in terms of e. How strange. It is weird how all these different like pieces are related to one another. So yeah, kind of where's this going, right? How bizarre. Below you see this graph of hyperbolic sine. And we can start to get an idea of maybe why it gets the name sine. Notice it passes through the origin, just like sine of x passes through the origin. Other than that, it doesn't look anything like the sine graph, of course. There you go, the graph of sinh x. Let's talk about hyperbolic cosine. So hyperbolic cosine, we're going to denote as cos h of x. But we're going to refer to that. Its nickname is just the way it reads, cosh x. Cosh x is defined as e to the x plus e to the negative x over 2. Notice the difference, we add instead of subtract in the middle. And that gives us the graph below. And you might see kind of at this point, like one small connection to cosine. The graph of cosh x passes through 0, 1, just like cosine passes through 0, 1. Otherwise, obviously, it doesn't look anything the same. There you go, the graph of cosh x. Okay, here are the rest. We've got hyperbolic tangent. Starting at the top, we're going to refer the nickname for hyperbolic tangent. We're going to call it tanh x, kind of like ranch. Okay, it's equal to sinh x over cosh x. Okay. Next is hyperbolic cosecant. That's 1 over sinh x. This is the most difficult name and the one I struggle with. Okay, so again, it's just kind of like as you read it, cosesh x. Up next, hyperbolic secant x. That one's a little bit easier to remember, sesh x. Kind of like, let's go have a study sesh. It is 1 over cosh x, right, of course. And finally, there's hyperbolic cotangent x, which we can call coth x. And you could say that's either 1 over tanh x or cosh x over sinh x. All right. You could break any of these down back into e to the x, e to the negative x, that sort of thing. Okay, we get it. Before we go any further, you might be wondering, okay, this is just getting weirder and weirder. There's all these bizarre names and nicknames. There's 6 of them. Maybe before we go any further, like what are some applications of the hyperbolic functions. Okay, so just really fast, here are 3 applications. There are plenty more. Let's check these out. The first one, this is kind of like the everyday application, is the catenary. The catenary would use cosh x. It describes the shape of a hanging wire between 2 poles. So if you thought of maybe like 2 telephone poles and the telephone wire or the electrical wire strung between them, the shape of that curve we call a catenary. And you would need to describe that using hyperbolic cosine of x. You would think that a hanging wire between 2 poles would maybe like form a parabola, but it doesn't. It has a completely different shape. It's still got that kind of curve, similar curve, that almost looks like a parabola, but it's not. It involves E, and there you go, cosh x, and we give it a different name, a catenary. I did a quick, let's see, I'll jump over here. I did a quick Google search, catenary. Computer's a bit slow right now. Let's search that. Images. Yeah, we get some good ones. So the first one here is these 2 posts and this chain. So a wire or even a chain strung between 2 posts, it's not a parabola. That forms a catenary. That's kind of cool. So we get some pictures of telephone wires. That's kind of the go-to example. But we see some other stuff too. There's like a trolley wire between 2 posts strung up above the tracks. So what happens is, just depending on the strength of the wire, that will, determine how much, how loose, that hangs, or how stiff it is. But in the end, you could describe it using cosh x. Okay. And then finally, you see, like, when you search for this, you'll see pictures of the St. Louis Arch. So I think there's a better one a little bit further down. Here, there we go. So the Gateway Arch in St. Louis, they designed this based on cosh x, like flipped upside down. So it turns out that that is an incredibly stable structure, because we get the same shape with a hanging wire or hanging chain. When you flip it over, the way that gravity works on this makes it incredibly stable. So it's pulling itself down right into its base very naturally. And so very, very stable object. So when they designed the Gateway Arch, they did it based on hyperbolic cosine, which is kind of cool. Okay. Back to the lecture document. So the catenary right there. Number 2, I thought this was kind of a fun one, the addition of velocities and relativity. I have not studied much relativity. There's special relativity and there's general relativity. In special relativity, which I think is what they're referring to here, you look at objects, like an observer watching another object pass by, right? So think of maybe a person standing watching a train pass. Well, maybe there's somebody, they see somebody in the windows of the train, like walking from one end of the train to the other, but then the train itself is also moving. So it turns out what they observe for how far a distance this person walks, and the time that passes, is different than the experience of the person who's walking on the train itself. I couldn't elaborate much more than that. Or you imagine, like an observer watching a spaceship. The spaceship is traveling near the speed of light. And then there's a person inside the spaceship that's like walking from one end of the spaceship to the other. So maybe they're like moving faster than the speed of light, to this observer, or maybe they're not. Okay, anyway, obviously I don't know much about this. It's been a while. Anyway, when you study relativity, you might have to add velocities. And to do that, you might use hyperbolic tangent x, tang x. Right. Finally, the third application is the tractrix, the path of an object as it follows directly after another object. So tractrix, it's the same root that we use for the word tractor. If you've ever driven a car or a truck with a tractor or a trailer behind you, you know very well that the trailer does not follow exactly the same path as the truck or the car. Whenever you make a turn, you have to make these wide turns because the trailer is going to cut inside the path that the car or the truck made. So you have to go out really wide to make sure that you don't, your trailer doesn't plow anything over when you make this corner. So it turns out that to describe the path of this object, you might use sec(x), hyperbolic secant. So that's kind of cool. Okay, I think we've introduced these pretty well. Let's stop here. We're gonna explore some examples and then get to the derivatives pretty soon.